Welcome to the Deep Dive. We're your shortcut to getting genuinely well-informed without feeling totally overwhelmed. Today, we're doing something a bit different. We're putting on our, well, detective hats, I guess, and digging into what's usually kept under wraps. We're looking at a patent application. Try to figure out, what the next big thing in solar power might be.
Yeah, it's pretty fascinating stuff.
This was from a company called Risen Energy Co., Ltd. The application number is US 22500-72161A1, and it just came out February 27, 2025. So our mission today, let's figure out what problem Risen Energy is trying to solve here, how they're actually doing it, and what it really means for energy for all of us in a way that actually makes sense.
It really is amazing how these dense, kind of legal-looking documents, they give you a real peek at the absolute cutting edge of innovation. And this deep dive into Risen Energy's work, it's a perfect example. You really get to pull back the curtain on these small, but, well, potentially powerful steps forward in renewables.
Absolutely. When we think about solar cells, most of us just picture like a flat panel on a roof, right, soaking up sun. But underneath that, there's this constant, really intense race going on for efficiency. And the core problem this patent is tackling, it says it right there in the background part, it's about a specific kind of high-performance cell, the heterojunction silicon solar cell.
That's right. The patent itself points to these heterojunction cells as being really critical for getting high conversion efficiency, which basically just means getting more electricity from the same amount of sunlight. And they see it as key for large-scale industrialization of the next generation of solar. So, yeah, they're a big deal. But the tech that exists, it has faced some tricky issues, especially around how well the different layers inside the cell connect and, pass the electricity along.
Ah, okay. So even though these cells were promising, there were these sort of weak links, stopping them from being as good as they could be. That must be incredibly frustrating for the engineers.
Exactly. Frustrating and inefficient. The patent specifically mentions things like poor contact performance between the transparent conductive layer and the groove slurry. Now, groove slurry, that sounds technical, but think of it as like a paste used in some older designs to make electrical connections. If that connection isn't great, it's like having a frayed wire. You lose energy, and you end up with low battery efficiency. So Risen Energy is trying to fix that specific problem.
Okay, that makes total sense. It's all about not wasting any of that precious solar energy, squeezing out every last drop. Now, to really get their solution, we probably need to understand this heterojunction battery or solar cell a bit better. Just in simple terms, we hear the jargon, but what is it?
Okay, yeah. Imagine a solar cell is like a really sophisticated layer cake, right? And its whole job is turning sunlight into electricity. The heterojunction part just means it uses different types of silicon layers stacked together. Each type has slightly different electrical properties. And putting them together in the right way creates this super efficient path for the electricity. So at the bottom, the foundation, you've got the main crystalline silicon layer. That's the workhorse. It absorbs the sunlight. The patent says it can be incredibly thin, too, maybe 2 to 250 micrometers.
Wow, okay. Thinner than a human hair, then.
Yeah.
And what about those other layers you mentioned, the intrinsic amorphous silicon, N-type doped, P-type doped? Why all these different silicon layers? Seems complicated.
It does sound complicated, but it's all about controlling the electricity flow very precisely. So you've got that main silicon core. Then they add these super, super thin layers on top, the intrinsic amorphous ones, kind of like a protective buffer layer. Make sure the contact is good, minimizes tiny defects. Then you get the N-type and P-type doped layers. Now, doping just means they add tiny amounts of specific impurities.
Okay, like adding a pinch of salt to change the recipe.
Exactly like that, a perfect analogy. Those tiny impurities allow the N-type and P-type layers to create an internal electric field. Think of it like a tiny built-in slope or a push. It makes the electrons, the electricity generated by the sunlight, flow very deliberately in one direction. Getting them separated and moving the right way is, well, absolutely key for making electricity. And then, of course, you need to collect that electricity, so they use transparent conductive layers, often made of something called indium tin oxide, ITO. The patent even mentions a specific mix, like 90% indium. These let light through but carry electricity. And then they add the metal electrodes on both sides.
Ah, so those are like the actual wires carrying the power out of the cell.
Basically, yeah. The transparent layers are the pathways inside. The electrodes are the final collection points.
Okay, got it. So this fancy silicon layer cake with internal slopes and pathways.
Yeah.
But you said even good pathways can have bottlenecks. So this must be where it gets really interesting. What's the aha moment? What's the key thing Risen Energy is doing differently to clear up those bottlenecks and fix the efficiency issues?
Right. The real clever part, the aha moment, is what they do after putting down those transparent conductive layers. They create something called a local reduction layer, and they do it using a technique called hydrogen plasma processing. And this isn't just, a tiny adjustment. It feels like part of a bigger trend, really fine-tuning that electron highway inside the cell, maybe finding smarter, cheaper ways to get more performance out of the materials they already use.
Okay, hydrogen plasma processing. That still sounds pretty sci-fi. Can you break down what that actually means? What are they doing to those layers? You said it increases carrier concentration.
Yeah.
What's that?
Okay, yeah, let's demystify it. Imagine using a really controlled blast of energized hydrogen gas. That's the plasma. It's like super hot, electrically charged gas. This plasma treatment basically microscopically sculpts or rearranges the very surface of that transparent conductive layer. Think of it like smoothing out a road at the atomic level, sweeping away tiny obstacles and creating these ultra-smooth, super efficient lanes for electricity, for the carriers.
Carriers being the electrons.
Exactly, the electrons carrying the charge. So it's not just cleaning the surface, it's subtly changing its structure to make it way easier for electrons to flow. It reduces resistance, improves that contact performance we talked about. It stops the electricity getting, kind of stuck or wasted on its journey out of the cell.
Okay, so it's about optimizing that crucial interface after the layers are already down. That seems like a really smart place to focus. And what kind of results are they talking about? How much better does this make the cell?
Well, this specific design, using that local reduction layer, lets them aim for some pretty impressive numbers. The patent mentions targeting high power density, something like 15 milliwatts per square centimeter.
Power density. So how much power you get from a certain area.
Precisely. More power density means you could potentially have smaller panels giving the same amount of power, or just more powerful panels overall. And they also talk about aiming for a high fill factor, maybe around 80%.
Okay, what's fill factor in everyday terms?
Imagine it's like how much of the cell's potential power actually makes it out without getting lost inside. A high fill factor means very little energy is wasted internally. It's efficient at getting the power out. So you put these together, the high power density, the high fill factor, and it leads to an overall cell efficiency potentially around 20%, maybe even a bit higher. And that's a really solid number in solar tech today, a definite step up.
That is genuinely impressive. Okay, so it's not just what it is, but how they make it, especially with this level of, fiddly precision.
Yeah.
How do they actually manufacture this thing? The patent must describe the method, right? Can you walk us through the basic steps, pointing out those key innovative bits?
Sure. Yeah, the patent does lay out the method. There's even a flowchart, figure 2, which helps visualize it. It starts, as you'd expect, with getting a really pure crystalline silicon layer, the base wafer. Then they texture the surface, which means making it rough on a microscopic scale, kind of like a tiny honeycomb that helps trap more sunlight, stops it reflecting straight off.
Yeah.
After that, really careful cleaning. They mention specific procedures like the RCA standard cleaning method. It just highlights how incredibly precise and clean everything has to be right from the start.
Makes sense. You need a perfect foundation before you start building those intricate layers on top.
Right. Absolutely critical. Then comes the layering process itself. They deposit those different silicon layers. You talked about the intrinsic amorphous one, then the N-type and P-type doped microcrystalline ones, sequentially on both the front and the back of that silicon wafer. It's like this incredibly careful microscopic painting job, layer upon layer. After those silicon layers are down, they deposit the transparent conductive layers again on both sides.
Okay, and then comes the special step, the Risen Energy innovation.
Exactly. Now comes that key part, doing the local reduction using the hydrogen plasma processing. And the patent mentions they can use something called a mask plate during this step. That lets them create a specific pattern. So they're not necessarily treating the whole surface uniformly. They can apply this electron superhighway treatment very strategically, only in the areas where it's most needed to maximize the benefit. And then finally, to finish the cell, they form the metal electrodes on top of those transparent conductive layers, front and back. Those are the final collection points to get the power out. The whole process is really geared towards optimizing that carrier concentration and contact performance, hitting those efficiency problems we discussed right at the beginning.
It's just amazing how much complexity and precision goes into what ends up looking like, just a flat solar panel on a roof. So let's zoom out then. What does all this technical detail actually mean for us? For someone listening right now, why should they care about this patent from Risen Energy? What's the real-world takeaway?
That's the crucial question, isn't it? And this innovation matters for I think several really important reasons that affect all of us. First, and maybe the most obvious, is just increased efficiency, higher carrier concentration, better contact. It directly translates to more sunlight being turned into usable electricity. So imagine needing fewer panels to power your house, or fitting more power onto, say, an apartment building roof, or even maybe integrating it into vehicles more effectively.
Yeah, that would be huge,
Yeah.
especially where space is limited. Or just getting more bang for your buck, like you
Yeah,
said.
exactly. And that connects straight to the second big point, cost reduction. It's almost always true that when solar cells get more efficient, the cost for each watt of electricity they produce goes down. So innovations like this help make solar energy more competitive against fossil fuels. It makes it more affordable, more accessible for people and businesses everywhere. It just speeds up the whole transition.
Right. Better tech literally means cheaper, clean energy,
Dude.
which is just a fundamental win for sustainability, isn't it?
It absolutely is. And that leads into the third point, the future of renewables. These kinds of technical improvements aren't just small tweaks. They are essential for solar power to keep growing and eventually become the dominant force in our global energy system. Every single technical hurdle we overcome, like the ones Risen Energy is addressing here, gets us closer to relying less on fossil fuels. It's part of tackling climate change, improving energy security, all of it.
And it also, I guess, highlights the global race for innovation, doesn't it?
Oh, definitely. This patent is like a little snapshot of that intense competition. You see companies like Risen Energy investing huge amounts in R&D, constantly pushing the limits, finding clever ways to squeeze out more performance. It shows the whole renewable energy sector isn't standing still. It's incredibly vibrant, really dynamic, with these complex engineering breakthroughs happening constantly, often behind the scenes. It's interesting. The whole energy transition we talk about, it's not just politics or economics. It's fundamentally driven by this kind of science and engineering, often hidden away in these complex patents. They really are the building blocks for what our energy future will look like.
And that wraps up our deep dive into this really fascinating patent from Risen Energy. It's genuinely incredible to see the kind of ingenuity that's going into making our energy cleaner, more efficient, piece by tiny piece, layer by careful layer.
It really makes you wonder, doesn't it? It raises a question for you listening right now. Just think about how many other innovations like this, maybe hidden in other patents, are happening right now. Innovations that are poised to reshape our world bit by bit, just like this one might. Things that could fundamentally change our energy landscape in just the next few years. We only looked at one piece of this huge puzzle today, but consider how all these small, incremental improvements documented in these technical papers, they all add up. They create these massive shifts in technology and eventually society, often quietly transforming things before we even fully realize it's happened.